Good morning everyone. Today we are going to present our project, Convolutional Neural Network-based Nutrient Deficiency Classification in Leaves of Elaeis guineensis. For the background of the study, oil palm nutrient deficiency can reduce the product yield, but normally the oil palm farmers cannot diagnose the disorder by themselves, so they have to send leaf samples to analyze in a lab, which takes time and money. However, there are relationships between leaf characteristics and nutrient content inside, so our project wants to use leaf appearance to indicate the nutrient deficiency. To do that, we use deep learning to classify leaf images that have nutrient deficiency. This can be further developed to be phone application to help oil palm farmers take care of their oil palm. The method of this project consists of two parts: data collection and program development. The first part, data collection. We collected leaves from 37 oil palm trees. Each tree we use front 17 for analyzing nutrients and front 25 for taking photos. For front 25, we set the camera as shown and take photo of the leaf one by one on white background. For front 17, we prepare the samples and analyze it by using two techniques. The first technique, ICP-OES, is used to find the amount of potassium, phosphorus, magnesium, and boron. The second technique, Jacq method, is used to find the amount of nitrogen.
The second part of our methodology is program development. Here are hardware and software specifications for this part. There are three main steps, including data augmentation, training, and testing. Since we have a small size of image dataset, the first step, data augmentation, makes more images from our original images through methods such as shearing, zooming, and flipping. After that is the training step. There are two image classification architectures used in this research. The first one is CS-BIO 2020, and another one is BetaNet. We trained the models with training set on 90% of the dataset. The inputs were images labeled with the nutrient ranges, deficient, normal, and excess. The training has been done for 200 epochs in CS-BIO and 500 epochs in BetaNet. And for the testing step, we use the trained model from training step to predict the range of nutrients from leaf images in unseen data or testing set. Using each model architecture, 5 models have been trained and tested separately for 5 kinds of nutrients. Moving on to the results, CS-BIO at 200 epochs and BetaNet at 500 epochs show satisfied results, having accuracies exceeding 70%. It can be seen that from 100 to 200 epochs, the accuracies of CS-BIO have increased except for phosphorus, of which accuracy decreased by 4%. Here are confusion matrices example of CS-BIO from testing step of 5 models, and from these confusion matrices, we can calculate 3 values including precision, recall, and F1 score to determine the efficiency of classification. These graphs indicate the precision and recall of CS-BIO models. It can be seen that the excess potassium is the lowest in both precision and recall. And these graphs show the precision and recall of BetaNet models. And finally, these graphs illustrate the F1 scores of CS-BIO and BetaNet. For CS-BIO, the F1 score will all over 0.65 except for excess potassium that is 0.48, which should be further concerned. For BetaNet, all F1 scores are ranging around 0.7 or more, meaning that there were no significant errors in prediction. Moving on to the discussion, firstly, according to the experiment, CS-BIO 2020 outperforms other previous architectures at 200 epochs, as shown in the bar graph. Although BetaNet obtained a better accuracy, it requires up to 500 epochs, so CS-BIO using less epochs to achieve high accuracy is a better fit for our data. From all 37 collected samples, there was no sample with phosphorus deficiency, making our dataset incomplete. Next, to develop this research into a practical mobile application, the accuracy should be more than 90 or 95%, which requires more data collection and experimentation with other model architectures. Then, I would like to state the benefits of our research. Firstly, our research has incorporated the data from lab results, which confirms our accuracies and is rarely or never seen before in other researches. Another point is that our approach can be applied to cover all main nutrients of oil palm, which is beneficial for practical use.
To conclude, this project collecting data of nutrient analysis and photo of oil palm leaves, then use deep learning to classify photo into 3 groups of each nutrient, which are deficiency, normal, and excess. The overall testing accuracy of 5 models is 77.2% for CH-BIO 2020 and 80.4% for Britannia.
Thank you for watching our video and see you soon. Bye!